This is Algebra 2, Unit 12, Lesson 9 on sampling variability and margin of error. Now, when we are working with statistical data, we want to know about parameters. A parameter is a fixed number that describes a population. So you say what percent of the population, what proportion of the population, what is the mean of or the standard deviation of the population. In reality, we don't know these numbers because we can't examine the entire population. You can't pick every single person in the world and figure out the mean, the standard deviation, and go ask them something about it. It's impossible. So what we need to do is to work with statistics. A statistic is a known number that describes a sample, but it can change from sample to sample. So when using samples from a large population to determine information about a population parameters, the samples must be randomly chosen. You have to not have any kind of bias, say one group over another group or anything. You want it to be randomly chosen. You must be of the same size, usually not smaller than 30. The more samples that you have, the more accurate your information is going to be. So that's what this says. The more samples that are used, the more reliable the information gathered will be. So if you are comparing things, you want the same size groups, you want to be randomly chosen, and you want to use as many as you possibly can. All right, now once you get all your samples, what do you do with them to figure out what your sample statistic is? Well, that's when you create what's called the sampling distribution of the sample statistics. That is a modeling process used to determine the best choice of samples from a large number of samples to represent a population. So you get a bunch of smaller samples, and then you pick the best ones that best represent the population. Choice is determined by examining all possible samples of the same size for a specific statistic. So if you're looking for the proportion, you would look at all the ones for proportion. You would look for percentages, that kind of thing. And then you would calculate the mean of that statistic. So you would take all the proportions and then find the mean of them. And a graph may be used to visualize what is happening with that statistics in relation to all the samples. Dot plots and histograms are common. Okay, so here's an example of a sampling distribution. If we are trying to determine the percentage of Americans that believe in life on other planets, we may obtain 100 sample groups randomly chosen with 50 people in each group. You can't survey every person in the United States, so you're picking 100 sample groups with 50 in each group. Okay, so then we're figuring out the proportion of people that believe in life on other planets from each sample group. So, for example, one group might be 19 out of 50 believe in life on other planets. So 19 out of 50 you would divide out to work out that. So, like, for example, 19 out of 50 is 0.38. So you would make a dot on your plot for 0.38. So that would be right here. One of those dots stands for 19 out of 50. There's also, then you do that for each group. So a second group of 50 people would be 21 out of 50, 32 out of 50. And you can see each group, there's 100 samples here, have been plotted, and it's determined and graphed on the plot shown. Okay, so the dot plot shows how the proportions from the 100 samples are distributed. The mean of these 100 is used as an estimate of the true proportion of the entire population. So you found the mean of all of the samples, and that is going to be the true proportion for the entire population, which would be, in this case, all Americans. So that's an example of the sampling distribution. Now, when you're doing a sampling distribution, you have to be aware of, in reality, it is not always possible to obtain all possible samples of a given population. So keep in mind that the sampling distribution of the sample population is a good estimate of the population proportion, and it will get closer and closer to the true population proportion as the sample size is increased. So the more samples that you have, the more it's going to be closer to the population proportion that you're looking for. And notice, the sampling distribution has the appearance of a normal distribution. So if we look at this, isn't this kind of bell-shaped? Yeah, it is. The more and more and more samples that you have, the sampling distribution of any statistics will be normal or nearly normal if the sample size is large enough. So the bigger sample that you have, the more it's going to look like a normal distribution. Once we have created a sampling distribution and arrived at our best estimate of the parameter of the population we need to reveal how good this estimate may be, statisticians form intervals surrounding the estimate which are called confidence intervals. Okay, it's how confident you are in your data. Confidence levels tell us the percentage of times the confidence interval actually contains the true population parameter we seek. So, for example, we could say we are 95% confident that the interval from 0.468 to 579 contains the true value of the population proportion. So the population proportion that we're looking for somewhere falls between these two numbers. We are 95% confident of that. Now, what we're going to be looking at is called the margin of error. The margin of error is an area around the estimate that you have. So whatever estimate that you came up with for your population proportion would fall, for example, right here. The margin of error is the distance from the estimate to one end of the confidence interval. So if you have a confidence interval, for example, this was 0.468 and this was 0.579, that would be the confidence interval. The distance from the estimate to each end of the confidence interval is called the margin of error. Okay, so that is within this region of the confidence interval. So from here to here is the margin of error, from here to here is the margin of error. Okay, so if you are given the standard deviation, which is the gamma symbol here, of a sample population proportion, the margin of error formula for a 95% confidence interval, that's the most commonly used one. The 95% confidence interval is 2 times the standard deviation divided by the square root of n. And n is the number in the sample size. So if you are told the standard deviation and the number of samples, the margin of error around your 95% confidence interval would be this formula. 2 times the standard deviation divided by the square root of the number. Okay, now to obtain the margin of error for working with a sample portion with a confidence level of 95%, say you're not given the standard deviation, what you would have is 2 times the square root of p times 1 minus p over n. P is the mean of the sampling distribution. So if you're given a mean of, you have a bunch of samples and you're given their mean, that would be the middle number. It would be p times 1 minus p. Now remember, p is the mean of the sampling distribution. 1 minus p would be the percentage away from it. And n is the sample size. So it's this formula for that. All right, so let's look at a couple examples using those values. If the sample mean is 25.2 and the standard deviation is 3.5 and the sample size is 100, what is the margin of error? Okay, so we are given the sample mean on this particular problem, okay, which would be that, and the standard deviation is the gamma symbol, the sample size is 100, so that would be n. So the margin of error that we would use the first formula. So the margin of error formula that we would use would be 2 times the standard deviation divided by n. Okay, so using that, 2 times 3.5 divided by, square root of n, I forgot the square root of n, the square root of 100. All right, so I would take my calculator and I would do 2 times, I'm going to use the alpha key so I can do it all at once. The standard deviation was 3.5. Whoops. Alpha key y equals number 1, with the wrong one. All right, so it would be 3.5 over the square root of 100, which is 10 anyway, but you get the idea. And your margin of error will be 0.7. Okay, so this is going to be 0.7. All right, now, we can say that we are 95% confident that the true mean is within the interval. So this is for a 95% confidence interval. It's going to be from the mean 0.7. So it's going to be 25.2 plus or minus 0.7. So the true mean is within which interval? Well, the mean is going to fall between 25.2 minus 0.7 minus 0.7, which is 24.5, and the other one is going to be, I'll just go up and grab this, change it to plus 0.7 is 25.9. All right, so that's what we've come up with. 25.2 plus 0.7 is 25.9. So your mean is going to, we're 95% confident that the population mean is going to fall, or the data is going to fall between these two values. We're 95% confident that the true mean is within that interval. Okay, so that's when we had the standard deviation. All right, so let's take a look at the last one. If the sampling mean proportion is 0.32, the sample size is 40, and we want a confidence level of 95%. All right, now the sampling mean proportion is the p. That's p. The sample size is n. So we want to use the other margin of error formula. We don't have the standard deviation, so we have to use the other one. Okay, so the other formula is the margin of error is equal to 2 times the square root of p times 1 minus p over n. All right, now p is 0.32, 32%, so what would be 1 minus p? Well, it would be 1 minus 0.32, which is 0.68. Okay, and then n, in this case, will be 40. So plugging this in, 2 times the square root of 0.32 times 0.68 divided by 40. All right, now I'm just going to put this in my calculator. 2 times the square root of, I'm going to use the alpha key again so I can see the whole thing. 0.32 times 0.68, and then divided by 40. And I end up with about 0.148. Okay, so the margin of error is 0.148. So over what interval are the plausible values for a true proportion? What would be, from where to where would we find the true proportion? Well, it would be the proportion that we have, the mean proportion, and then it would be plus or minus 0.148. So it would be 0.32 plus or minus 0.148. Okay, so if I do 0.32 minus 0.148, I end up at 0.172. And then if I do plus, change this to plus, and I get 0.468. So working that out, I end up between, I am 95% confident that this would fall between 0.172 and 0.468. That would be where the sampling mean proportion is for the plausible values for true proportion. It falls somewhere between these two values. Okay, so that is margin of error and sampling distributions.